That's what this is right here. So I'm going to come over here and put power on what they call the coil. It's going to pull that plunger up and let the fluid flow. And then when we take that power off, what's the spring going to do? It's going to push it back down. This is pilot operated. So what we do is we come over here and lift this up. And what we're actually doing is we're using fluid to come up here and pick this up or push it down. This is not a really good drawing. But what we do with a pilot operated valve is we operate it with the pressure that's already there. Now, what we do is we come up, the way we represent the symbols of the valve itself is we use these blocks. And you can see it down at the bottom. So this is the symbol for this valve. So what we do is we put our ports coming in and out. First of all, we draw the valve in what we call its normal position. So what we got is this is a normal position. So you look at this side right here. This right here has the piping coming into it. So this would be the ports. So this would be a two-port valve or two-way valve. Everybody okay so far? Right, but look at the one on the left. So this is a two-position valve. And what are we going to do with this thing? We're either going to open it or we're going to close it. So this would be the image of what we call a normally closed valve. Now, if you're in electricity, you've got to learn that in fluid power, open and close are two different things. So in fluid power, if we close a valve, we prevent it from flowing. If we open a valve, we allow it to flow. In electricity, if you have a closed circuit, so you got to learn the difference. There's a difference in fluid power. So what you got to picture in your mind is you got to picture these two blocks. Now the outside, these guys right here never change positions. Oops, sorry. So these things never change positions. And what we do is we're going to shift this thing over. So what's going to happen when we shift it over, then this is going to come over there and it's going to line up with the pipes, and this over here is going to be over here. That makes sense. So what you got to picture in your mind, they draw the valve in its normal position. So this would be what we call a normally closed valve. And then when you turn it on, in your mind, you got to see that symbol shift over. And when we shift it over, what lines up? Well, that arrow lines up now. So now the fluid can flow in the direction of the arrow up to our actuator. And this would be a symbol of what we call a normally closed, what would we say? Two-way, two-position, normally closed valve. Now we hadn't showed you how we shift that thing. And this is the way these different operators work. We can shift that thing manually, or we can shift it electrically, or we can shift it with fluid. And that would be what we call how we operate it. The book calls it actuators, but I call them operators. We can shift it manually, or we can shift it electrically, or we can shift it with fluid pressure. We call that pilot. So we can shift it with the pressure of the fluid itself. Makes sense. So this would be what we call a two-way, two-position valve. And then we'll give you then part of it is then we give you how it's operated. So if I was to operate this manually, we would say it's two-way, two-position, normally closed, manually operated valve. Oh yeah. We can have 5 ways. Go ahead.
That's normally open.
This is normally closed because this is the normal. It's drawn in the normal position. What I've done is I've shifted it over. So you're looking at this. That's not the normal position. This is the normal position. See the little pipes coming in from the top? Now this is a normally closed valve. Now to open it, I have to shift it, right? And what you've got to do in your mind is you've got to see those squares shift. So we draw what happens inside a position, we draw it inside a square. So we're either going to have 2 squares or 3 squares. We don't have more than 3. We'll always have 2, right? You understand? At least 2. We can have a maximum of 3. We add a center position. And all we do on the left and right, we'll put the symbols of the operators, which we'll come in and look at later on. But it's going to be manually operated. We'll have spring operated. I forgot that one. That would be mechanical, right? Yeah. And what type of valve is this? Well, it's a valve. You know, it's just we don't control the rate of the flow with these valves. All we do is we're going to shift the position, right? You understand that? The first valve we'll look at is what we call a check valve. Somebody run into a check valve. Now, no matter how it operates, and it really don't make any difference to us how it operates, the symbol for the check valve is the same. It's the little thing on top there. It shows the pipes coming in. And then it's got a V, and then it's got a circle in the center of it. So if we push it into that V, it's going to block it. If we push it away from the V, it's going to let it flow, right? Anybody have one of these? No, don't? I got a couple of them going on right in here, right now. This is what your heart valves are. They're check valves. It's check valves. So when your heart is pulling it in, that's one valve open, right? The other valve is closed. And then when it pushes out, right, you understand, it opens up the other valve. So it's really, really neat. It's pushing out one side and pulling in the other. We don't want the part that's going out. So your heart pumps. What would happen if you didn't have a check valve? Your blood, instead of going out, it would do what? Yeah, this is what happens a lot when people get electrocuted. Their heart goes into fibrillation. Their heart goes into fibrillation. Their valve gets out of sync with their heart, which means you create no pressure. And what do? If somebody don't get if they don't get your valve, then your heart back in sync with each other. And that's what they bop you with it. So they bop you with it. Then if they can get that back in sync, then you're okay. If they don't, you die because you don't create any pressure. So you got 2 check valves in your heart. So what does a check valve do? Well, it allows fluid to flow in one direction and blocks it. I got one of these on my house. If you don't have one on your house, you need one. Because what would happen if you don't have one on your house and they bust a big water line and they cut the water off, what's going to happen to all the water that's in the house? It's going to go back out that pipe. And then when they turn it back on, what are you going to do? You're going to pay for your water twice. Because your water meter don't run backwards. So you probably need a check valve. Probably a pressure regulator too. You probably got that on the house. So sometimes we use gravity. Sometimes we use flaps. Sometimes we use balls. We have what they call a poppet, which is basically kind of a ball and a poppet are basically the same. So you can see the poppet's got kind of a V shape and rounded on the end. And then it plugs that hole up. So when pressure comes in on this side, what's it going to do? So if flow tries to go in this direction, what's it going to do? Well, it's going to push that poppet or push that ball into that socket and it's going to block the flow. When it tries to come this way, what's it going to do? It's going to push that out and it's going to flow once it overcomes the pressure of the spring. So anybody got a shop vac? You probably got one of these in your shop vac. So if it gets full of water, got that check valve in there, and what would it do? It floats up and stops it up. So that's gravity. A lot of times we use a spring because if you have a gravity check valve, then you're always going to have to put that thing on. Yeah, vertical. If you got a spring, then what can you do? You can turn it around, but you're going to have to overcome the pressure of the spring. So these are some check valves. The one on the bottom right, this is the way your compressor works. Most of your compressor uses a little flap little piece of metal. I don't know if you ever took a compressor apart. That's always just little flaps of metal. The metal's bigger. It's usually copper, and that's bigger than what it sits on, and it just flaps back and forth. And these are all just check valves. I don't know why this there it is. Bicep, you got a check valve on your tire. So what can you do on your tire? Put air in, but the air doesn't want to come back out. Now it's the valve got a problem. That's a check valve. So it lets you put air in your tire, but it prevents that air from getting out. And that's what that one is right there. And this is the check valve. I didn't notice that. So when the fluid comes in this way, it's going to turn the butterfly, right? You understand? If it tries to go the other way, what does it do? Blocks it. I thought it was an operator. That is a check valve. It's got a butterfly feeding on it. This is a heart valve. The center one on the bottom. So that's your check valve. So it lets your heart beat. And they go in different directions, right? The one opens when you're expanding, and it closes, the other opens when you push out. So y'all have check valves. We have check valves in the heart. So none of these animations on there, I just found them today. So this is one of your simpler valves. And what's the symbol for this? No matter how it works, that on the top is the symbol, but we got one little more thing that we need to put on it. If it's got a spring on it, then what they do is they put this little line on it like that. That means it's got a spring on it. Huh? It's also a symbol for spring. We don't have any resistors in here, so that if you see it on our drawing, it's a spring.
I always wonder how they control hydraulic jack. Because if you use the same pressure.
Now what's that check valve in there? So when you push down, it opens up the check valve. And when you raise it back up, the check valve closes. So it doesn't let it flow back into your reservoir. So you got that reservoir in there, right?
Right.
Same thing true. That's not true on the brakes. Your brakes don't have to do that.
But I was curious how, at some point, like the pressure that lifting up the car would be greater than what you push down. I know it'd be harder as you go along. So I always wonder why that pressure did not come back.
Because the check valve gets it on the way up. And then you got a bypass that bypasses the check valve, right? You understand? So when you go over there and turn that little thing, all you're doing is bypassing the check valve and now letting the fluid do what? Flow back into the reservoir. That's all you're doing. So you got a check valve when you twist that thing in, which is probably a needle valve, because you can control that flow pretty. So you can let your car down fast or slow. So you raise that thing out. In fact, I've had it all the way out. It is a needle valve. Then you pump it. It's got that check valve that don't let it do what. So you got a lot of pressure going down, and when you come back up. Are we okay? Spring return. Everybody okay on that? So what we got to do is we got to understand that if it's got a spring on it, and most of them do, because if it didn't have a spring, then you would always have to mount it in the same direction, right? You understand? But if it's got a spring, then we can mount it anyway. So most of them have a spring. And if it takes 5 psi to operate it, then you're going to lose 5 psi going through the check valve. Everybody understand that? You got to overcome that. So you got to maintain that 5 psi here, right? You understand? Everybody okay? So this is Nancy's right here. So she was looking at this and just said, okay, what about the top one up there? How much pressure would it generate? So this is so that's the spring. What she's got 5 different pressures that operate the check valve. By the way, this is the symbol of a pump. and it's the symbol of a hydraulic pump. A compressor uses the same symbol, but on pneumatic, that triangle you see right there, it won't be filled in. So that's basically the big difference on the symbols. Is that hydraulics, if it's got any errors, they're going to be what? They're going to be filled in. If it's not filled in, then that's going to be pneumatic. So a compressor would have exactly the same symbol, but that the error would not be filled in. So what about the top one? How much pressure would that generate? It's going to generate as much as the pump will do, because they're all, the flow is against the air. The flow is seeding. The flow is seeding, right? You understand? Yes or no? Yeah, the flow is pushing the ball into the seed. It won't flow. So how much pressure? We don't know. Because, right? You understand that? Now look at the bottom. On here, they're pointed in the right direction. So the flow is against the air, and you can see what's going to happen when it flows. What's it going to do with that ball? It's going to push it back. So how much pressure would our pump generate here? Right. But I don't know what she's got across the top. 35 psi. Right. No, the first one's 5, and then once it's open, it's open. Then once that 5 gets through, that next one's got a cracking pressure of 10 psi. So now we've lost what? 15 psi. Y'all understand that?
Okay, so we subtract it from our total.
Well, here we don't have a total because, well, how much pressure do you have on the right-hand side? Well, all you got is what we call back pressure. There's really no pressure on the outside, right? So the pump would generate enough pressure to open up all those valves. And so what that means, if I've got, now normally we don't put 3 check valves. I've never seen 3 check valves in series with each other. But this is basically the law of electricity for a series circuit, if y'all have DC. So the sums of the voltage dropped in the series circuit has equal to the applied voltage. Well, that's true here. So what we have for a check valve is we have what we call a cracking pressure. And that would be the pressure required to push that through. That make sense? Yes or no? Okay? So what about on the top one? No flow. What about on the bottom one? No 5. The other 2 won't open. As soon as that top one opens 5 psi, then it goes over this. Yeah, it goes. Now we have 0 psi. We have 5 psi on the left. We have 0 psi on the right. So the 10 and 20 would never open. Y'all understand that? Yes. I don't know why she did. By the way, that on the right hand side, that's the symbol of a reservoir. Most people call that a tank. So on a hydraulic system, we have to have a tank, right? Shuttle valve. Shuttle valves are self-actuated, which means they deal with pressure. So if you notice, we got the V on both sides, and right now it's in its normal position. So the flow would be now. Remember, we deal with pressure. So if I come over here and route this valve, by the way, so this is the operator. What we're operating this valve, and what would you think that looks like? Don't see a man doing push-ups. Lever. So that's a lever operator. So you see this a lot on earth moving equipment. Don't have power supplies on them. A lot of your big ones and more expensive ones has computers and everything and have proportional controls. But a lot of your older earth moving equipment, it's either go or no go, right? And they have that. It's not a lever operator. So that's a lever operator. So right now, both these are, so look what happens. By the way, this is E. What do you think E stands for? Close. What do you call the air when your car gets through with it? What do we call that? So that's your exhaust, right? So that's the exhaust. P would stand for pressure. So that's our pressure, right? And then your working port's called A. So your P for pressure, E for exhaust, and then A and B would be your working port. So how many ways does this valve have? 3. It's a 3-way valve, 2 positions. So what I'm doing is I'm looking at this right here. That's 1, there's 2, there's 3. So I got 3 ways. The valve is drawn in its normal position. So this is a 3-way, 2-position valve. Okay?
Yeah, I'm just using that look on my face.
So right now, here comes my pressure. So this is my air supply. I know it's pneumatic because why? It's not colored in, right? You understand? So everything that requires the pressure, and this pressure is coming in and pushing on these valves.
I got a question. When we see those little P2 square, every time we have a port or wave, they will always be present
No.
inside the block.
No. What we're doing to look for the number of ways is we're looking for these lines coming out like that. That's the number of ways.
Okay. So the waves are.
Now, if you see a T, it means it's blocked. If you see an arrow, it's going to flow. Okay, you understand? So right now, when I follow this red line over there, okay, so when I follow this red line, so here's the red line. It goes up to that T. It goes up to the T. Where can the air go? So where can the air go? Where can the air go? Say nowhere. It's blocked. It's in that T. It's no arrow. So to make it flow, we got to see an arrow, right? So when I come up there and push this, what you got to see in your mind, and this don't happen, you got to see those squares change position. You understand? So what happens is this one moves down here. So right now, if there's any pressure in this, so this is the spring. This is a single acting cylinder. We already looked at this. How do I know it's a single acting cylinder? It's only got one port, right? You understand? So if there's anything that was in here when that spring, there's nothing pushing that cylinder. There's nothing pushing it. So if it was out like that, it comes back in. If we didn't give that guy a way back to outside air, it wouldn't do anything, right? You understand? So what we're going to do is we'll come over here, and I'll do this in green. So anything that was in here would go that. Which way is it going to go? It can't go that way, so it's going to go what? This way. Okay, and it comes over here. Do I have a path? Yes. So it goes out here and it's exhausted. So if that cylinder was extended, it let it do what? It let it retract. Because if I block that fluid in there, it wouldn't retract, right? You understand? So what's going to happen? I should have left that up there. So I'm going to leave the air supply all the time. So what you've got to visualize is when I push that operator, these squares, this square right here comes where? Down here. And then this square right here moves down to there. So what I have now, I have this, right? You understand? And then this is blocked off. So what's going to happen now is the fluid's going to flow through here. It's going to go up. And it's going to do what? Push that thing and it's going to extend. Now what if I came over here and operated that one? Well, it's not going to do anything because this one this one happened first, right? You understand? So that means now the guy on the right can't do anything. So he can pull it and try to retract it, you push it up, try to extend it, he's blocked off. Okay, so this would be a sample where I could operate something from 2 different locations, and whoever gets to it first gets control of it. I mean, what you wouldn't like that. You're over here trying to do something. You got that thing pulled up, and you put your hand in there. And another guy over there comes over here and pulls it and drops it down on you, right? You understand? So we can only operate this from one position. So what would happen if I let go? Well, if I let go, what's going to happen? The valve is going to shift back to its normal position. The valve, this guy here was extended. So it was extended, so it's going to retract. This is back to its normal position. It's going to exhaust and let it retract. Now, what would happen if I came over here and hit this guy first? Well, if I hit this guy first, then what's this ball going to do? This ball is going to shift over to the other side and block this guy off. And this is why it's called a shuttle valve. And this is automatic. It's operated by pressure. And what this guy does is this guy allows us to, one person, we have two operating stations, but only one of them at a time can operate. It's also called, it also does what we call OR logic. So this is a logic, this is a hydraulic logic. So what do we mean by OR? Either person A or B can operate, but not A and B. A and B cannot operate. So this does OR logic. And they call this a shuttle valve. And we got a lab on this. It's about A, I think. 8 is the lab we'll do our logic on. If you looked at the lab book, 8's going to be changed out. So we're going to put a new lab in there. I give y'all labs out, by the way. Shuttle valves. Are we okay? And that's the symbol of a shuttle valve. How do they do it? Well, I don't really care. I mean, it does it. How they do it, I don't really care, because all I need, if I know the symbol, then they're all going to operate the same, no matter how they do it, right? Does that make sense? Huh?
Right in the middle.
This is the symbol of the shuttle valve right here. We okay? Huh? And this is a shuttle valve. This is animation. And you see it here. They're using a flap. So when this guy comes up, the flap moves over to the left. When this person pushes at the valve, as long as the guy on the right has his control passing fluid, the guy on the right, on the left, is blocked off. So this, and what's neat here, they're showing the what in the symbol. Showing the valve shift back and forth. Yeah. So this is a self-actuated valve. OR logic. If you're looking at the PowerPoint, OR logic is not up there, I just say. Valves are identified by the type of control, spool operated, which is by far the most common. So all the valves that we have in the lab are spool operated. Poppet, reciprocating disc, and rotary, which is what's shown. Are we okay? I don't think I got pictures any better of this. I think this is out there. They show y'all different ones in the textbook. Well, all this is a rotary shown. But we've already seen what a poppet looks like. A reciprocating disc is just a disc that's got slots cut into it. And then when you move it, what does it do? It lines up. This is the ones we're dealing with. This is called a spool valve. And it got the name spool because when we draw it like this, it kind of looks like a spool that you wound thread on. Spool thread. And somehow we position that spool to control the flow. Now this would be manually operated, or I don't know what's over here. It looks like a manually operated. So what a manual operator looks like this. It comes over, and then it has that up there. And it almost looks like the thing, doesn't it? And it's drawn in this position. So this is a normally open valve. Because notice the little lines on the outside line up with the arrow. So this is a normally open valve. And you can see what happens. They do a good job with it here. So right now, fluid's gonna go in, it's gonna do that, right? You understand? And then when I come over here and move it into this position, what's gonna happen? Yeah, it's gonna be blocked off. Now, I don't know what they're gonna do with the fluid. Somehow they're gonna exhaust it somehow. This wouldn't be actuating a cylinder. So if we actuate a cylinder, we're gonna have to let the fluid get out somewhere. We're just turning water on and turning water off. Then we wouldn't need an exhaust, right? Everybody okay? Wrong way.
If the line's not on the outside, then you know it's not normal. Those lines are not present.
These lines right here show you the normal position of the valve. The ones that come out of there. That shows you the normal position of the valve. And they don't have to be, they could be on the right or they could be on the left, but that shows you the normal position of the valve. And that's what we're going to connect up to. So if I was going to control something, then I would take this right here, right? This right here would be pressure, and this right over here would be whatever I'm trying to control, like a motor. So a motor usually don't need an exhaust. A fluid power motor, a pneumatic fluid power motor usually don't need an exhaust. We don't have to bring it back because why? It's got its own exhaust on it. So it sits there and spins. So this would turn a pneumatic motor on and off. Now a hydraulic motor, we're going to have a tank, right? You can't spill it out. We can use this to control a cylinder because once we push that fluid out, we got all that fluid in the back of that cylinder. We're going to have to do what? Get it out of there somewhere. So we would have to have an exhaust, but this would be a good one to control a fluid power, a pneumatic motor, not a hydraulic motor, a pneumatic.
But what I'm saying, I have seen guys manufacture those boxes, no outlet.
But you hadn't seen it.
Okay.
Not unless you're just looking at symbols like this. Because what you've seen is probably seen this. Let's draw it like it would be in real life. So I would have my symbol, okay, and then I would come over here and I would have this. I would have this, and then I'm going to put two T's right there. And then what I'm going to do is I'm going to take this, and I'm not just going to draw it right there. I'm going to draw it off to somewhere, and I'm going to draw it up to a motor. And down here, I'm going to take this, and I'm going to take this back to pressure. And that's the way it would work. If you don't have those, all we do on the symbol is just show you the normal position, but this is where you hook your things up, right? You know what I'm saying? And we draw these things, we don't draw these things sideways, we don't draw them upside down. The industry standard is pressure and exhaust on the bottom, and your working ports are going to be on the top. And here they're showing manually operator spring return. So what they've done here is this we don't know. I don't know if it's normally open or normally closed because I don't have what? Yeah, you don't show me where the actual ports are. So we're drawing just the little lines, but in real life, those little lines are going to be what? Going somewhere. Okay, guys, let's take a 2-minute break. Hold on, 2 minutes. So this right here would be how many ports? 4 ports. By the way, so this is hydraulic. So P is pressure, T is what? Tank, and then A and B would be what we call the working ports. Those would be the guys that actually move the next one. And when we draw it, we put the working ports on top, and then we put the pressure ports and the tank ports would be on the bottom of the symbol. But normally, when we actually have the valve, this is 2 position. This is a 3-position valve. Can you see? Yeah. And what does it do in the center position? It blocks everybody, right? So if I was to draw the symbol for this valve, so the normal position, normally on a 3-position valve, the normal position is the center position. So we draw like this, right? Everybody okay? In fact, I need to make this one over here bigger. In fact, let me make it a lot bigger so I don't have any problems. So what we do here is notice when it's in the center position. I paused it. So right now, so when it's in the center position, everything's blocked off. So I'd come over here and do this. We're okay so far? And then when we go to the left position, it looks like it's sending, so up here we would have A, B, and down here we would have pressure and tank. Okay? And then what I would do is, I did it again and paused it. So when we're in the first position, we're routing out port A. So I'd come over here and so we're taking pressure out port A. So as soon as I do this, it's going to stop, but I got it now. So we do this. That makes sense? Then if I come over here, what would I do? Let's swap around. That would be the symbol of this. Of course, I needed to go up to the top, and this would be a 3-position valve. 4-port, 3-position, or 4-way, 3-position. But that's not the way we say it. This is the way it's nomenclature's got. We start off with the number of ports, so I'd say what? 4. And then I say the number of position, 2. Then we say what? I know it's backwards, but that's the way they do it. So we would call this a 4-3-way valve. I know it's backwards, but there's nothing we can do about it. That's the industry standard. That's the way you would order it. So we'd say this is a, we don't specify if it's a spool valve or whatever. We say it's a 4-3-way valve, 4-3-way valve manually operated. If we put a spring on the left-hand side, we'd say it's manually operated spring return. Are we okay? So that would be the industry standard if you're going to order this thing. We start off with a watt. We start off with a number of ways, right? Then we put a slash, then we put the number of positions, and then we say what? So this would be a 4-3-way valve. Y'all like that? I'll make it easier. So it's not like if you don't like your name, when you get older, if you don't like your name, what can you do? Change it. So this would be like before you're 18. You're stuck with your name, right? So we can't change this name. So they start off with a number of ways. Then we put a slash. We put the number of positions, and then we put ways. That's the way it would be written. The way we say this is a 4-3-way valve. So we got a bunch of valves up there, and different symbols. They're all manually operated or lever operated. The first two on the top, these are spring return. So notice the one on the top left. There's nothing over there. We get over there. on the B. So B, the thing would be retracted, right? You understand? And then when I operated it, it would do what? Something's going on here. That's wrong. Huh? Yeah, B's wrong. A's right, B's wrong. Why is that? Why is B wrong? Because if you let go of the lever, what's going to happen? It's going to move that thing to the right. Okay, you understand? And it's drawn in its normal opposite position. So what do we mean? Is somebody going to stand up there all the time and do that? So that's wrong. B is wrong, A is right. So, y'all understand what I'm saying this way? Huh?
Because the arrow's pointing down.
No, because the spring's right there. So what would be the normal position with the spring on the right hand side? What has to be the normal position? It's got to be pushed to the left. There's no way in the world that symbol could be right. Because the spring is on the right hand side. If you let go of the lever, what's the spring going to do? It's going to push it back to the left. Well, that's the normal position. The normal position without you doing what? Without you touching that thing. So the one on the right, if you let go of that lever, which way is it going to go? It's going to shift that way right there. It's got to. The spring is pushing it to that way, right? Y'all understand? So look at A. So there's A. A is right, B is wrong. So what did they do? Well, they moved the stuff around, right? You understand? Yes or no?
They moved everything to bring the level right.
Where at? Yeah, they're both wrong. Yeah. So to me, they both look wrong. So C is right. Well, if it was a locking lever, it would have another symbol. We called it a detent. So what I would do is I would come over here and do the same thing, and I'd put a little notch in there. And what that means, that would be once you moved it, it would stay in that position. The way these are drawn, guys, if we let go of that thing, well, it looks like on some of these. So this one looks right to me. This one looks wrong. This one looks wrong. This one looks okay. This one's definitely okay because it's in the center position. So anytime we have a 3-position valve, then the normal position is going to be where? In the middle. And then, of course, we got springs on both sides. So what happens if you let go of the lever down here on B on the bottom, it's going to automatically do what? Go in the middle. So some of these look wrong. I don't know where. Is this in the book?
No, number on A and B, I think it's all swap.
The exhaust doesn't make any. It doesn't really make any difference. What we're going to do is normally they on pneumatic valves. Normally they don't put the P, they don't put the E, they don't put A. They use numbers, and the pressure port is always 1, and the exhaust is usually on the right of the pressure port. Well, no, on pneumatic they number them. On most hydraulics they use letters. They use P, T, A, B. On pneumatics, on the valves they use 1, 2, 3, 4. So your working ports are going to be even, and your pressure ports are going to be odd. Huh? Yeah. This was scanned out of the book. But like I said, I don't know if they revised it or not. Normally, your normal position will be which way the spring pushes. Y'all understand what I'm saying? Does that make sense? I don't know why A says corrected. I don't really know why that's not there. Now, the 3-position valves, these are all correct. Except for these. What's wrong with these? Well, here's the pressure ports on the top. What we do, and I'll show y'all some diagrams. The industry standard way of drawing fluid circuits is from bottom to top. The pressure, now when you hook them up, it don't make any difference if you put the pressure port on the top or the pressure port on the bottom. But what we do when we draw it, industry standard says your pressure's on the bottom. So the way we draw these is they're drawn like this. So what you do is you have your pressure your power source on the bottom, then you have your control, and then your actuators on top. This is the industry standard way of drawing a fluid power circuit. Now when you get out there and hook them up, then normally all your ports are going to be on the bottom of the valve, right? Because it's going to mount on the base. And they do that because you can buy the valve and you can mount it on the base, or you can mount it on the manifold. You understand what I mean by manifold? Right? Just like the manifold on your car. It's got one common. So what we do is we have one common pipe inside that manifold that carries the pressure, and then we got one common pipe that handles the water. The tank or the exhaust. And then you have taps on the side of the manifold for the working port. So you have where it screws into the side of the manifold. And that's very, very popular because you save so much space, right? You understand? Instead of having to put a base, you can cram those things in there right there together, right? You understand that? So if we went over there on the manufacturing lines, every one of those guys use a manifold. Yeah, but the ports are standard sizes. And so if you make sure you bought one manifold, so if you needed 5 ports, on one of your valves you needed 5 ports, and you'd buy a manifold that had 5 ports. And then the valve that didn't use it, it would fall into a slot that would be blocked off. Understand?
Trying to word it right. The ports that I need to operate, all the ports need to operate off the same port.
Oh yeah.
Common manifold.
For that common manifold. And this is very, very popular. Like I said, both of our manufacturing lines over there, the Festo line and the Amptro line, uses the manifold. So all the valves mount on that manifold, they're right there together. You don't have to have that extra space. You bring one pipe in that's got the pressure, you share the exhaust, you share the pressure. It's a big pipe, because it's got to handle a lot of flow. And then on the side of the manifold, you come out, each one of them got the actual working port that you hook up out to the side. I wish it was over there. If y'all remember, I'll try to take a picture. I'll show you. And that's very common. Even on the big Fanuc robot we got over there, it's got fluid power on it. It's got this big old manifold mounted on top of it. And all the valves just mount on that common manifold. And in that way, they only got to run one pressure port to the manifold and one exhaust or one tank port to the manifold, right? You understand that? We use a basic manifold over here to make circuits real easy to hook up, because the manifold that we have is got check valves on it. So if you pull a pipe out, it automatically seals. It's kind of like a quick disconnect you buy for a hydraulic or pneumatic system. Quick disconnect. Well, that thing on the end's got a check valve on it, right? You understand? So as soon as you disconnect it, the pressure closes the valve, and you bring it up, and you push it in, you literally force the check valve open. So the end of that little socket pushes the check valve away. So I'll run into those quick disconnects all over the place. So all our fittings are quick disconnect fittings, because we're going to be doing piping. This is where the problem we had with the hydraulics is the quick disconnects on hydraulics. Look, they're very similar to the ones that you get for a pneumatic system. Very similar. except they're high, they're real high pressure, but they work the same way. You don't ever pop that thing off where you don't hear anything, well, that check valve. Well, when that happens in hydraulics, what squirts out of it? We got a little hydraulic fluid, so we had problems. So solenoid operated, y'all see how the solenoid actually works. So that the valve that I passed around, it's solenoid operated. So that's when you see the 3 prongs on the side. Most of them have manual overrides on them. So if you had a screwdriver or something, if you look, it's got a little thing in there you can push in and actually manual override it. Can you see? So the manual override. So we can literally take a screwdriver or something, take that to the brass thing and push that thing in and manual override. Now, of course, anytime you manual override, what's not here to actually upset you. You got to understand the consequences of manual override. Taking something away from automation. Got all these safety features built into it. Keep it from getting killed. You go in there and manual override. We had a guy got killed out in the top of No. 8 blast furnace when I was out there. It was a continuous cast furnace, and it had so they brought a big old belt up to the top, and they had to keep pressure on there. So what they do is the belt would drop into a hopper, they'd open up the top door, and then it would close, and then what would they do? They'd open the bottom door and let it fall down into the furnace. And they was having problems with one of the doors. I don't remember which one. And they went in there and they locked it out. They did all that stuff. They disconnected and told the guy to go in there and push in the relay. And he pushed the relay in for the bottom door. They didn't lock that out. And it killed it. So we're talking about that. You know, you need to understand the consequences of the manual override or what's going to happen. I'm laughing. We worked out at number 4 galvanizing line, and they had the strip welder where when they ran out of a roll, they would cut it and weld it together. And they had big clamps that would come down and clamp onto the sides of that thing so it wouldn't move. And we was out there working on those things, and it was running. That thing was running like 700 feet a minute, and we were pushing in a relay, and luckily they was running a narrow strip, and I was bringing that side clamp down. And what would happen if they had run a wide strip? What would happen? If they clamped down on that strip, and that thing's running 700 feet a minute, Rich would have been hiding. You got to understand the consequences of what you're doing, because you can definitely get people killed. So just about all our automated, even relays, have manual overrides on them. Thank goodness. We had radio-controlled cranes, and they were radio-controlled. They didn't have cabs on them. They were radio-controlled. Those same things would get stuck out there in the middle of the house. You had to move them. Well, what did we do? Well, we climbed up on the thing. We went in there and manually override the thing and run the crane manually. So what was it? All the wrong drawings. So this is the way it works in pneumatics. So normally we don't put exhaust. We don't put, and they cross. So notice it goes what? It goes 1. So on the bottom you'll have 1. It'll be on the right hand side. And then you go up to the top, it'll be 2. And then you do what? Come down to 3. Go up to 4. And then if you had a 5, you would come down. And we'll talk about a 5-port valve. You won't run into 5-port valves in hydraulics, but we do run into some 5-port valves in pneumatics. What they do that thing for, it allows us to control the speed of flow on different. Are we okay? So this is a 2-position 4-way valve. We call this a 4-2-way valve, right? 4-way valve more common in hydraulics and pneumatics, and that's not true. I can come over here and look at these diagrams. I don't know where that came from. But this is one of the lines, for one of the stations on the Siemens over there. And every one of these are wrong. Well, they're all 4-way valves. All 4-2. So I don't know where that came from. You said 4-way valves are more common in pneumatics. 5-way valves are more common in pneumatics than hydraulics. But we use four-way valves all over. Especially if you're gonna do what? Yeah, if you're gonna extend the track, you almost gotta have a four-way valve because, if you're running a double acting cylinder, you gotta have at least a four-way valve because you gotta swap the exhaust and the pressure, right? You understand? So I don't know where that came from. So notice every one of these are what? Four-way valves. Solenoid, so that little, we'll look at these later on, but the little box, the little rectangle on the left-hand side, that means it's solenoid operated. And then the one right up above it means it's got a manual override on it, right? Understand? Then on the right, now notice every one of these, if they got a spring, they're pushed in the position the spring is pushing in. So that's what gave me problems with those on those. I need to go back and look at those. So the one on the left, that would be a 4-2-way valve, solenoid operated with a manual override. The one to the left, that would be a 4-2-way valve, solenoid operated manually, manual override. Double solenoid, we'd say double solenoid operated. And then that would be what the rest of them are. So that little thing on the side, that's the manual override that you can do what? Push it back and forth. Without electrical power, by the way, you don't want to push against the solenoid. So if you're gonna manual override these solenoids, you need to cut the power to the solenoid because you could burn the solenoid up by forcing that thing back in. So I need to drop that off, right? I didn't put that down. Who put that? Wasn't me. So this would be a five-way. This would be a what? No, four-way. So we'd say 4 3-way valve. And then we put the operators on the outside, how we operate the valve, how we move it. This would be a closed cylinder. This is very popular in pneumatics. Normally in pneumatics, if we can't vent the pressure, right? You understand that? A lot of times in hydraulics, if we're not using it, we just send it back to tank. Pneumatics, we don't ever just pump it back out to air because you lose your compression. So anytime we're not using the air in the pneumatic system, we're going to block it off, right? Does that make sense? PEAB. And of course you can see it up here. Now, this is kind of misleading because it looks like what? It looks like it's that. But in actuality, what they don't show you, and it could be a 5, so this is where we get our 5-way valve. The symbol is telling me that inside the valve, these two ports are connected together. And this is where the 5-way valve comes. So if we got a 5-way valve, it's going to be a pneumatic valve, and we're going to have 2 exhaust ports.
Did you want to say?
Well, this is exhaust. Normally when we use exhaust, we're talking about pressure, but this could be tank. It only have 1 tank output. But what they do, and if you're using the spool, you're going to have 2 exhausts because you got to shift it out this way. When it shifts, you got to shift it out the other way. But what they do inside the valve, they'll put those 2 exhausts or those 2 tanks together. So if they don't do that, then by George down here, they would show you a 5-port valve. The symbol shows you the actual number of ports that you have got to screw something into. Y'all understand? But I can see where this is confusing because when you look up there at the actual spool, you see what? You see 5. My drawing was awful, guys. I would fuss at y'all if y'all did that. And this is what they showed you right here. So this is what they're showing you. So inside the valve, those 2 exhausts are what? Piped together. Now we do sometimes bring those two exhausts out. And that's the only time you get a 5-port valve, is that they don't pipe it inside. Y'all understand? And this is still a 5-port valve, because when I hook up to it, this is a 4-port valve, because when I hook up to it, I hook up 4 ports. So the only way that I've ever seen a 5-port valve that's in pneumatics, it is if they do bring both the exhausts out. And what the advantage of doing that, for one thing, is that the exhaust on the left is going to have more friction on it than the exhaust on the right, because it's got further to travel, right? So that's one advantage of having 2 exhaust ports. Another advantage is that we can throttle each one up. Throttle means we can control the flow. And we'll talk about that. So on pneumatics, if we're going to control the flow, we control the exhaust. We'll talk about that too, and why we do that. So what would this be? Yeah, so here they're sharing it, even though they show one exhaust, because that's all we connect up to it. Inside the valve, they actually have to do that because the spool is rerouting the exhaust. So when it's shifted one way, you got to have an exhaust over here. When they shift it on the other, you got to have exhaust over here, but it's actually ported inside. So all we would hook up to this valve was we have 3 pipes, 4 pipes. A lot of our valves, the exhaust is actually inside there. So some of our valves, we don't even have an exhaust we hooked up. It's inside the valve. I'll have to. Okay? Okay? I'm going. 5-way valve, more common in pneumatics than hydraulics. Here they're talking about high pressure and low pressure. I think they're talking about, and they're putting an exhaust in the center. I've never seen a valve like that. Here's some of our valves, and here's the name. So directional control, two-way valve. So that's the industry, right? 2-2. So it's 2 ways, 2 positions. Closed. So this is normally closed. The second one on the left, this is what? 2-way valve, normally open. And the third one, this would be a what? 3 2-way valves. So notice the number of ports. They start off with the number of ports, 3. We put a slash, put the what? Number of positions, then we use the term what? Guys, if it's confusing, all I can say is I'm sorry, that's the way it is. Closed in the normal position. Well, that's a normally closed valve. A 3 2-way valve, open in the normal position. Don't understand that? Yes or no? 3 3-way valve, closed in the neutral position, which is the center position. Normally they say center, but here this, wherever they got this from. I think I did this. I think I got these actually out of the Pesto book. A 4 2-way valve. Now, 4 2-way, right? You understand? Then we have a 4 3-way, closed center. Then we have a 4-3, exhaust neutral position. This is, some people call this a floating center, center. Why do they call that a floating center? So remember, your actuator is going to be hooked up to 4 and 2. One's going to extend it, one's going to retract it. It's up to you which way you want to hook it up. It depends on what you want it to be in the neutral position. Does that make sense? Well, if I lock that thing, if I lock it and I don't let the pressure move inside my cylinder, the cylinder is going to be frozen. Now here, it don't make any difference which one's the exhaust, which one of the pressure. If I push it one way, it's just going to wrap back around, right? You understand? So my actuator is I'm going to be able to go up there and grab it and do what? Huh? Move it. Right? Y'all understand? Yes or no? That makes sense? So some people call this a floating center because your actuator actually floats. It has the ability to move. If I lock the exhaust, then it's going to stay extended. If I lock it if I lock the exhaust, then we can't retract it, right? You understand? If we lock the extended, then we can't retract it. So if we leave pressure on one side, then we could actually, if we had, we could actually start the thing moving and stop it. And if we block both, if we had this one right here, if I had this one right here, I could start it moving, and then I could let go, and it would return to the center, and the actuator would be locked. Why? Because it couldn't exhaust, and the fluid could not move. So the fluid inside the actuator is going to have to move. So if you're pushing fluid on this side, then the fluid on the other side's got to be exhausted, right? You understand? So that closed center, what the book is calling the neutral, this would lock it. This would allow it to float. And this would be two exhaust ports. So that's a 5 two-way valve. What's the 5? Oh, we've added the exhaust on both sides. These are some other things we'll look at. We have what we refer to as a service unit. So the surface unit on a pneumatic system, what do we have to do? Normally we have a filter. Are we okay? No, I just put this one up there. I mean, like I said, this is the filter. What's this? The regulator. Allows you to regulate the pressure. Anybody know what this is? No, this is not a valve. We're controlling the pressure. It is a valve, but this is the valve that we use to regulate. So normally, when we run compressors, the most popular compressor out there is what we call a reciprocating compressor. And instead of making that motor run all the time, what do they do? They have what we call a maximum pressure and minimum pressure. It's got a band. And what's happened when it drops below the minimum pressure, the pressure kicks off. Right, you understand? And then it comes up and goes up to a maximum pressure and kicks off. Well, where do your tools? What would happen if you ran your tools inside that thing? Well, all your torque and your speeds and everything would be constantly changing. Right? So what we do is if I want to, and if I tried to run it while the compressor's running, my air would be really jerky. Right? Because the compressor's pushing it in, pushing it in, pushing it. When I'm out there spray painting, I don't want it to go, right? When I'm out there using my impact wrench, I don't want it to have a bunch of it and then slow down and speed up and slow back down. So what we do is our tools, if it's below 70, then we usually operate, most of your commercial air tubes is rated at 60 psi. So what do we have something that regulates at 60 psi. So we set our regulator at 60 psi, and then we should never get, as long as our compressor can handle the flow of our tools. If it can handle the flow of our tools, then that means we'll have a constant, nice, solid pressure. If your compressor is running all the time, you need a bigger compressor. You're running tools that compressor was not designed for. Y'all understand that? Your compressor should cut off. You set out there, you're still using your tool 60 psi. When it drops down to 70, your compressor has a higher flow rate than your tools. So it can handle your tools, but it still has the ability to do what? Kick back up and fill it back up, right? And you keep a constant pressure on your tools. If you have a constant pressure on your tools, you get a constant torque. Man, that would be awful trying to spray paint when the pressure was constantly doing what? Oh yeah, and also, oh good gracious. The problem, and a lot of times we leave off right there. In fact, if I was working in spray painting, we'd add more to it. We'd have to have something to make sure we get no moisture in the system. even though the filter takes care of a lot of the moisture. The filter not only takes care of getting, don't let goop get into your system, it also, water is heavier than the air, so when it hits that, water goes to the bottom. A lot of pneumatic systems you'll see, they'll have a big old U every once in a while. And at the bottom of the U, they have a wash, a drain. It does. Most of your filters have drains in the bottom of them. Some of them are electric, so they'll automatically drain every once in a while. This on the right is a lubricator. This is where we would run, if you're running all our valves, and our valves are not self-lubricating valves, you will definitely run a lubricator. And all it does is just keep, of course, just a little bit of misty oil into the air all the time. Well, it depends. Self-lubricating valves are a lot more expensive than regular valves. So what you find out is a lot cheaper to have a lubricator than it is to buy a self-lubricating valve. So, yeah, they could put self-lubricating inside your car. So my compressor is self-lubricating, and sometimes they actually lubricate the compressor. So our big compressor over there has got a oil tank on it. My compressor at my house is a Craftsman. It don't have it. It's self-lubricating. It's sealed or Teflon. So this is what they call the simple symbol. So this right here indicates this is the filter, this is the pressure gauge, this is the lubricator, this is the complex symbol, this is the actual symbol of a filter, this is the symbol of a pressure regulator, and this is the symbol of a lubricator. And this is the symbol of a mister, guys. I have no idea what a mister is. Oh, it's a mist separator, right? So that would just be another water filter. And we call these things service units. Our service units look like this. So we don't have a lubricator on our system. But we got everything else. We got a filter, we got a regulator, and we got a pressure gauge. Your regulator don't show you your inlet pressure. Your pressure gauge on your regulator shows you your outlet pressure. So a lot of times you'll have I got a pressure gauge on my compressor, and then I got a pressure gauge on my regulator. Are we okay? So I think these are covered in another chapter. Why we went ahead and stuck it in here was because we're going to use them over there. These are our operators. So manual operator, you okay there? Lever operator, hand operator, cam operated, solenoid operated, manually operated. The manual operator is just a generic operator for manual. Spring, everybody okay there? Pilot. So what do I mean by pilot operator? Fluid actually operated. Yeah. Button operated, foot pedal operated. And this is what I was talking about. If it's got detent, what does detent will do? Once you move it in there, it'll lock it in that position until you move it again. But anytime any manual operator's got a detent. Now they don't show the electrical wiring, so we got a completely different print that shows you how the things are wired electrically, right? So on the solenoid, we got to have wires going to the solenoid. But on the fluid power drawing, they don't show anything electrical, right? You understand? All they say is that that's solenoid operated. All it is that little rectangle with a watt to it, a slash. Now, it's becoming very popular on pneumatics to have a solenoid, and I'll let you show y'all the symbol. Here's some more. These are all the same thing, right? This is the guy right here. This is a solenoid pilot operated valve. The problem we have is your little solenoid cannot generate a lot of force. But we might have to control a lot of force. And the bigger force and flow you gotta go, that spool starts getting really, really big. And all of a sudden now you got a cylinder, your solenoid can't push that through. But what can the solenoid do? Well, the solenoid can open up a little tiny valve and let the pressure that's already there do what? Come up and push the spool. And these are common. In fact, every one of them over on our lines are like that. I don't know if they use the symbol or not. Yeah, this guy right here. Notice the way Festo does it. So they got the solenoid on the left, and they got the what? Pilot symbol. And this is the way Festo does that symbol. So what the solenoid does, it's got that pressure there already. It just opens a little tiny valve, opens it up, pressure comes in, does what? Hits the side of the spool, and does what to the spool? Shifts the All right, Nancy, bye-bye. Right. So that means this is the manifold inside this dashed line here. And then the valves mount on the manifold. So you see they all share the pressure. So here's the pressure. This is a disconnect right here. So notice it's got a detent. So we use this to actually turn the air off and on. Okay. Lock lever. It's called a detent. So it'll stay in. So if you turn it off, it'll stay off. If you turn it on, it'll stay on. That's what the detents are there. You see that? Frankie, what you doing back here, man?
Are we going to use this stuff? No.
No, that's for mechanical.
Oh, wait, how do Matt gonna fix that stuff?
No, our lab is next door. So this is a disconnect, so it gives us the ability to turn the air off. But we've got ball valves up in the seat also. So make sure when we're piping the circuit up, we're going to turn the pressure off, right? What the M means, so you see we have circuits, so this is one circuit, and the A means this is the actuator, so that's actuator 1, so everything that controls actuator 1 is down below it, and then everything that controls actuator 1 starts with a 1. So notice this was 1M1, 1M1. What do you think that is? Well, 1M is the M's are solenoid. And this is the first one in the control circuit. It's the first one on the left. If we had another solenoid control valve that controlled this thing, it would be 1M2, right? Everybody follow that so far? So the letter M is talking about solenoid, right? These are valves. So this is 1V1. This is circuit 2, this is 2V1, this is circuit 3, this is 3V1, this is circuit 4, that's 4V1. That makes sense?
No, you didn't write on
I didn't write on it. I was using it as pointing.
Okay, but Matt, just to understand, where that actuator is, everything below it
Controls it.
controls it or it controls it?
The actuator is the output. So that would be like me saying my engine in my car is controlling me. So the engine in my car is the actuator. And then everything that's controlling that engine would be down below it. So the actuator don't control basically anything. The actuator is doing the work.
And all that.
It's controlling the actuator.
Okay.
It determines when it extends, it determines when it retracts, it determines what speed it moves at, right? Does that make sense? Yeah. So everything that controls that actuator is down below it. So we start off with the pressure source. We go up, there's no curved lines, all the lines are what? Straight, just like in electronics, when you draw schematics, we don't do loops. Everything's straight, right? You understand that? And we draw the pressure sources at the bottom, and then we do what? Then we work up to the actuator. The actuator's at the top. Everybody okay with that? These are flow control valves. We'll look at it in a minute. So this is a 4-2-way valve solenoid operated spring return, right? This is a double acting cylinder with a magnetic piston. So that little old U right there means that that thing's got a magnet on it. You won't run into many of these on hydraulics, because hydraulics usually have to have steel cylinders. But in pneumatics, we use aluminum cylinders, and aluminum does not impede a magnetic field. A magnetic field applies to aluminum like it's not even there. Okay. And then what we do is we literally got sensors that we can put out on the side. They're called reed switches in Hall effect, that we can tell when it's fully extended and when it's fully retracted. We got some valves over there. I'll have to show y'all that, and they're operated by that magnet. But we can put that thing up there on that cylinder, and when it extends, it'll open the valve. And then we can use that to do something else. If we didn't have a magnet to do that. These are what we call flow control valves. So flow control valves do exactly what they say they're going to do. What did I say? What are they called? Flow control valves. So when I follow this up, I want to do a different color, Rich. So I'm going to do pressure. Let's do it in red. So here's my pressure. We'll just use this first one. It's in its normal position. It's going to go through there. It's going to come over here, and it's going to bypass the flow control. It's going to push the check valve open, and it'll come up here. And what's it going to do to the cylinder? So this cylinder should be retracted when we turn this on, because this is the normal position, right? You understand? And then, of course, what's going to happen to the exhaust on the other side? Well, the exhaust on the other side is going to come out. It can't go to the it can't go through the check valve. It's going to close the check valve. So it's got to go through the flow control valve. It's going to come up, go back through here, go down, come down, and do what? The exhaust. Now, in pneumatics, on a double action cylinder, if we're going to control, and so what do you think the flow control valve does? It controls the speed, because it controls the flow. So the pressure determines the force, the flow determines the speed. Does that make sense? Okay. So what we're doing is we're making the exhaust go through the flow control. We call this meter out. Now, pneumatics, we meter out. So what we're doing is we're deliberately creating a back pressure. So we're not letting the exhaust go out fast. We're making it slow it down. If the exhaust slows down, then it's going to take a while for the cylinder to retract. So even though you're pushing on the other side, you still got to overcome the back pressure, right? Now, why we meter out on a double acting cylinder? Now, on a single acting cylinder, the only thing you can do is meter in, because the exhaust, you use the same pipe for exhaust, right? You understand that? Why we meter out pneumatics is pneumatics are compressible. So that means if my cylinder is turned like this, and I'm metering the input, then the cylinder would just fall down, because the air would just uncompress, right? You understand? But if we meter the exhaust, then you've always got back pressure, so you can mount the cylinder any way you want. Another thing, what happens with pneumatic cylinders is that you push that pressure in, the piston moves. Well, as soon as the piston moves, you lose pressure. You got to wait for the flow to repressurize. So what happens on a pneumatic cylinder, if we flow control in, the thing is going to be jerky. It's real jerky. If we meter out, then the cylinder moves what? Real slow. So pneumatics we meter out on a double acting cylinder. So we make it go through the flow. We bypass the pressure, and we make it go through the flow on the exhaust. And we call that meter out. And the term is when in doubt, meter out. And so meter out works with hydraulics. Hydraulics, we don't have that problem, but we do. The problem with hydraulics is if I've got that cylinder pointing down and I'm metering in, and it's got a negative weight down here, it's gonna be cool. You say, well, fluid is uncompressible. But the problem is, if you got any air anywhere in your line, now you're pulling that air, instead of pushing that fluid out, you're pulling that air in, and you get air in your system. So normally we try to meter out. Hydraulics, you say it doesn't really make any difference, but the rule of thumb is what? When in doubt, meter out. Single acting cylinders, you can't. You got to meter in on a single acting cylinder. Got to. So if we shift this thing the other direction, then what we got to understand is everything swaps, right? So we move over here. I'm just going to move the ports over there so we can see them. But what it's actually moving is the valve. So this port right here would shift to here. This port right here would shift to there. Oops. And then my pressure would come in here. So now what would happen? Then the fluid would come up through here. It's going to go up here now, right? It's going to go this way. Then it's going to do what? Go through the check valve. It's going to come over here and do what? Push it out. Then the flow is going to come through here. This is going to block it. It's going to go through there. And then it's going to come over here and go back to the exhaust. And that's what you got to visualize in your mind. You got to visualize those what doing what. Yeah, and this is what I've done for you over here, right here. I've traced the flow, so my pressure's going here. Took me a little while to do this, guys. And when I go to the next one, so I'm showing my solenoid is pushing me to this direction. And then this is what literally happened. But it don't happen on the, you gotta visualize it doing one. Shifting. You gotta visualize it. It's not gonna shift. Well, that was done with Microsoft Paint, by the way. So right now the solenoid's pushing it to the left, and we turn that solenoid off, and then this one does what? And this is what you got to visualize in your head. Is you got to visualize that whole thing going on. And that's the hard thing about it, but that's the way it is. So they draw the valve in their normal position, right? You understand? And then you got to realize that whole thing doing what? Shifting over and everything realigns. So you can see this. That's not animation. That's done with 2 PowerPoint slides. And then I brought it up in Microsoft Paint, cut it out and pasted it. Ready to go. We do have a package that I need to install on my computer. It's called Fluid Sim, which is really neat. Because when you animate it, you actually see what? You actually see the valve shifting, which is pretty neat. But on a diagram, on a diagram for the fluid power, they're going to draw it in a normal position, and that's what you got to visualize in your whole head. What? It moves. Sure. And notice how it flows through, the exhaust goes through the flow control.
So those are manual check valves that lock it.
No, they're automatic. They're manual. Check valves are those are automatically operated. We don't touch them suckers. They automatically do what they're supposed to do. They're controlled by pressure. Oops. So what we live with this, and then we got to manually see that in our head. That whole thing does what? Shifts over. By the way, this is really neat. Festo does not use spring return; they use pilot return. So on the right hand side, it literally pilots that thing and allows and uses pressure to return it. Where the Amatro line, they use spring, they either use solenoid return or they use spring return. So, took us a little while to figure that out because we'd never seen it before. But then you realize and you get into it, you say, well, it makes sense that they can pilot return it, right? Yeah, you say, well, and it makes, and this is why the manifold is so much, so more complicated. So the manifold, Festo valve, so the Amatro lines, the manifold is on the bottom. On the Festo line, all the porting is done through the valve, and the manifolds are on the outside. Really, really slick. So all this porting, the valves all line up. You just stay in there and you clamp them in on the manifold. What's nice about that is all the valves are ported the same except for your working ports. And if you needed to add another valve, you just break it apart and do what? Stick another one in there and clamp it in. If you buy a manifold, you're going to buy it to control 8 valves or something like that. And if you, for some reason, you want to change it, then you'd either have to set that thing off on a base by itself because once your manifold is full, it's full. But what's nice on the Festo, the way those things work, it's really, really neat. By the way, this is the symbol. Technically, that's the true symbol. Technically, we call that a silencer. But guess what? Just about everybody calls it. They call it an exhaust. I'm sorry, they call it a muffler. But technically, it's called a silencer. And it does exactly what your muffler does. Anybody ever cut a muffler open? Besides for the catalytic converter, it has all these old veins sticking all over the place. And what it does, it makes that pop go all different directions. So all the pop doesn't get to one side at the same time. And that's all the silencer does. It just gets all these little tiny holes all the way down, right? You understand? And it makes that pop come out and spread out, and it don't make near as much noise. So those are silencers. They can be ceramic or they can be brass. The Festo line uses both of them. So if they're ceramic, they're just made out of thousands of little ceramic beads, and then they're epoxy together. The same thing true with the brass ones too. There's a bunch of brass beads, and they just basically weld them together or even melt them together. And you've got all these holes that it takes all different types of directions. Are we okay? And then this is what I wanted to show y'all exactly. And notice one of them's Festo, one of them's Siemens. But yet they still follow the same. By the way, these B's, these are sensors. So those that show up on our, 1B1 and 1B2, one of the sensors is going to sense when it's extended. The other sensor is going to sense when it's what? Retracted. And that's so B's are sensors, A's are actuators, M's are solenoids, right? B's are valves. And that's the same thing. So if I could get this from Festo or I can get it from Amatro or whoever, or Siemens, and the diagrams are what? Amatro, and I said Siemens. This is an Amatro line. So Amatro was made here in the United States. So this is the Amatro line. Drawn by Siemens, but this is the diagram for that. Are we okay? Anything else on there? By that guy in the center, this is using Bernoulli's principle. Notice it's choked off. That's the vacuum generator for the line. And that's the symbol for that. We call it a Ventura vacuum, but it actually uses Bernoulli's principle, where if you speed it off, the pressure does what? Goes down. It actually sucks air in. That's it. Yeah, M is solenoids. A is the actual actuators. This is a rodded cylinder. So the rodded cylinder, I think I showed y'all that over there, actually works on magnetics. So the piston actually has big, nice magnets out, and then the carriage on the outside just clamps onto those magnets. So this is what we call a rodded cylinder. Now, what's the advantage of a rodded cylinder? The stroke. Yeah, the stroke. You're not limited to the stroke. You can make these things have 10-foot strokes if you want to. It'd be almost impossible for me to have a piston cylinder with a 10-foot stroke. Right? You understand? Unless the dang rod is used. All right? So a rodded cylinders, both lines, both the Amatro and the Festo line, all have wires. And this right here is these right here are cushions, and this means they're variable cushions. What a cushion does, and these are in cylinders. We'll talk about this is okay now. Just to explain the system. What a cushion does is that it's got a rod that sticks out of the back of the cylinder, and when it comes flying through there, the rod jams into a hole. And then we control the flow through that hole. So what happens is the rod don't bump up against the end cap. So we call those cushions. And then a variable means we got a little tiny little screw on the side that I can adjust that slow down at the very end. So what we do is we use fluid to do what? Slow it down right before it hits the cap. The cap is actually the end that's away from the rod, and then the end on the end of the rod, they call that the head.
There's actually no cushion there.
Some of them does put a piece of like rubberized material in there, but they don't call those cushions. When they say cushions, those are actually, I don't know if I've got a drawing of it or not. I know I got it in, but so the rod actually comes through. It's got so the cylinder would if we looked at the actual piston, it would actually look like this. Then it'd come over here to have this. And then over here we'd have the rod, and then right here we would have this. And then what happens, when back here at the very end, we got a hole. And when this thing comes flying back in there, this is full of fluid. And then what we got this little tiny hole that comes back and brings it back over to here. And then we got a needle valve in here. So what we do is that when it hits that hole, if the fluid didn't move, then it would just stop, right? But when it hits that thing, now it's trying to push that fluid that's in that tube back there, and then it goes back through that little old tiny trough, and we're controlling that with a little needle valve, and then it wraps the fluid back into the piston. And those are called adjustable cushions. A non-adjustable cushion, that hole it would still have that path back around there, but you couldn't adjust it. So that air up through there, that means it's adjustable cushion. So when you look at our valves, you see at the very top of both sides, you're going to see two screws that you use to adjust those cushions. So when we go over there and do the inventory. Okay. In hydraulics, we have another worksheet that I want to do in class. We got 3 circuits that I want to do in class to get y'all ready for what's actually on the test. Like I said, a lot of the questions, you can see, so we got symbols. Symbols are on the test. All the symbols we went off through tonight are going to be on the test, right? You know what I'm saying? All of them. Pretty much. And then solving but the way the test is different is that you're going to have to solve for area. And I wish that's the way the worksheet was worked out. So with the worksheet, what they did is they did what? They gave you the area on every one of them. So you didn't have to solve for the area. When you get a piston though, they're not going to tell you the area, they're going to give you the diameter, right? We call it the bore and the rod. So let's work on these. Let me find them. I want to get that. And then after that, we'll go and try to inventory our kits. Here they are.